Hello friends, welcome to my lecture on harmonic functions, harmonic conjugates and Milne's method. Let us first define a harmonic function. A real valued function f x by of two real variables x and y is said to be harmonic in a domain D if it is a solution of the Laplace equation and has continuous partial derivatives of second order in D. This means that del square f is equal to 0 and f x, f y, they are continuous functions of x and y. It follows that real and imaginary parts of an analytic function in a domain D are harmonic functions in D. In our previous lecture we have seen that the real if you take an analytic function f z equal to u plus I b, then if z is equal to x plus I y, u and b are in general functions of x and y, and u and b satisfy del square u equal to 0, okay, that is u and del square b equal to 0, that is u and b are solutions of Laplace equation, and moreover u and b have continuous second order partial derivatives. So, the real and imaginary parts of an analytic function in a domain D are harmonic functions in D. Now, let us look at conjugate harmonic function. If two harmonic functions u x y and b x y satisfy the Cauchy-Riemann equations in a domain D, that is u x is equal to b y and u y equal to minus b x, then u and b are said to be conjugate harmonic functions in D. The real and imaginary parts of an analytic functions are therefore conjugate harmonic functions, because they are harmonic functions and they are related by Cauchy-Riemann equations. So, two functions are called conjugate two harmonic functions are said to be conjugate harmonic functions if they are related by Cauchy-Riemann equations. Now, let us take an example. If we know one harmonic function, the other harmonic function can be found out using the Cauchy-Riemann equations, and we can then find the corresponding analytic function. So, if you have u x y equal to e to the power minus x into x sin y minus y cos y, then first we see that this function u x y is a harmonic function of x and y. Now, you can find the so in order to prove that u is harmonic, we need to show that u is a solution of the Laplace equation, that is del square u equal to 0, or we can say u x x plus u y y equal to 0, and moreover the second order partial derivatives are continuous. So, here you can see u is e to the power minus x into x sin y minus y cos y, it is infinitely differentiable, okay. All ordered derivatives of u exist, okay, with respect to x and y, therefore, second order partial derivatives of u are continuous. So, we just have to show that u is a solution of Laplace equation. So, in order to prove that u x x plus u y y equal to 0, let us first find the partial derivative of u with respect to x. If you differentiate u with respect to x, what you get is u x equal to e to the power minus x into sin y minus x e to the power minus x into sin y plus y e to the power minus x cos y. If you again differentiate u x with respect to x, you get second order partial derivative of u with respect to x, that is u x x equal to minus 2 times e to the power minus x sin y plus x times e to the power minus x sin y minus y e to the power minus x cos y. Similarly, if you differentiate u with respect to y, you find the partial derivative of u with respect to y, keeping x constant, we see that it is x e to the power minus x cos y plus y e to the power minus x sin y minus e to the power minus x cos y, and then again if you differentiate u y with respect to y, you get u y y. So, it comes out to be minus x e to the power minus x sin y plus 2 times e to the power minus x sin y plus y e to the power minus x cos y. Now, you can see if you add this second equation u x x equal to this and u y y equal to this expression, then u x x plus u y y equal to this term will cancel with this term will cancel with this, and this term will cancel with this, and we will get u x x plus u y y equal to 0. So, u is a harmonic function of x and y, okay, in the whole complex plane. Now, let us find the corresponding harmonic function b x y. So, we will have to use the Cauchy-Riemann equations. So, we know that u x is equal to b y and u y equal to minus b x. Okay. So, we have the value of u x with us. Okay. Let us put the value of u x. So, we get u x equal to e to the power minus x sin y. So, e to the power minus x sin y, then we have minus x e to the power minus x sin y, then we have by e to the power minus x cos y. So, this is the value of u x, and u x is equal to b y. Okay. Now, in order to find b, let us integrate this equation with respect to y, but this is partial derivative of v with respect to y. So, while integrating b with respect to y, this equation with respect to y, we will have to keep x constant. Okay. So, this implies b x y is equal to, since we are keeping x constant, e to the power x minus x, e to the power minus x will remain unchanged. Integral of sin y is minus cos y, okay, and then we have minus x e to the power minus x, integral of sin y is minus cos y, then we have e to the power minus x integral of by cos y dy. Okay. This gives us b x y equal to minus e to the power minus x cos y plus x e to the power minus x cos y plus e to the power minus x. Now, let us integrate this. So, we have integral of integration by parts we are doing. So, by times sin y minus integral derivative of y is 1 and we have sin y plus a function of, because we are integrating with respect to y assuming x as a constant. So, constant of integration will be a function of x, let us write phi x. So, this will be b x y equal to minus e to the power minus x cos y plus x e to the power minus x cos y, then we have by e to the power minus x sin y, integral of sin y is minus cos y. So, we will have plus e to the power minus x cos y plus phi x. Okay. Now, we will have to use, in order to determine this unknown function phi x, we will have to use this second equation. Okay. So, in the second equation we need the derivative of v with respect to x. So, let us differentiate this equation with respect to x. So, when we differentiate this with respect to x, we get derivative of e to the power minus x is e to the power minus x into minus 1. So, we get e to the power minus x cos y, and here cos y times derivative of x is 1. So, we get e to the power minus x, then derivative of e to the power minus x is e to the power minus x into minus 1. So, we get minus x e to the power minus x, and here derivative of e to the power minus x is e to the power minus x into minus 1. So, we get minus by e to the power minus x into sin y. Here also we get minus e to the power minus x cos y, and we get d phi y dx, because phi depends only on x. Okay, this e to the power minus x cos y and e to the power minus x cos y will cancel, and we get the partial derivative of b with respect to x as e to the power minus x cos y minus x e to power minus x cos y, and then we get minus by e to the power minus x sin y plus phi dash x. This d phi by dx let us write as phi dash x. Now this Vx is equal to minus uy, okay, and since Bx is equal to minus uy, okay, the value of Vx is equal to minus uy, and uy we have found here. So minus uy is what? Minus x e to the power minus x cos y. Okay, let us put the value of uy. Okay, we have uy equal to x e to the power minus x cos y then we have by e to the power minus x sin y and then we have minus e to the power minus x cos y okay. So we have uy equal to this. Now let us put the values of this is equation, let us call it as 1 and this as 2 okay. So Vx equal to this value and uy equal to this value. From 1 and 2 what do you notice? Vx equal to minus uy okay. So the Vx equal to minus uy will give you what? This term will cancel with this term okay, this term will cancel with this term when you use Bx equal to minus uy, and this term will cancel with this term, and what we get? Phi dash x equal to 0. So from 1 and 2 phi dash x equal to 0, which implies phi x equal to some arbitrary constant c okay. So what you get? Vxy equal to Bxy is this okay, this Bxy, this was the value of Bxy, this term you can cancel here itself okay. So Bxy equal to x e to the power minus x cos y plus by e to the power minus x sin y plus c okay. So we get this value of Bxy using phi x equal to c. Now Fz equal to u plus ib, let us find the corresponding analytic function. So now we have the value of u equal to e to the power minus x sin y minus y cos y, e to the power minus x sin y this is u okay. And what is b? b we have found b we have found to be x e to the power minus x cos y x e to the power minus x cos y plus by e to the power minus x sin y plus c okay. So hence the corresponding analytic function Fz equal to u plus ib is equal to e to the power minus x into x sin y minus y cos y plus I into x e to the power minus x cos by plus I by e to the power minus x sin y plus I into c. Okay. So, now what do we get? Let us combine, let us write e to the power minus x here and then see what we have here. So, we have x sin by x times sin by plus I cos by and here we have minus by cos by. So, minus by times cos by minus I sin by. Let us look at it again, e to the power minus x here, then x we take common from these two terms. So, we get x times sin y plus I cos by, and here we write minus y times cos by minus I sin by, right. Okay. So, we have e to the power minus x, and here what I do, I take I outside. So, I into x, and then this is cos by minus 1 upon plus 1 upon I sin by. So, cos by minus I sin by it will be, and here this is already cos by minus I sin by. So, minus by cos by minus I sin by. What do we get? So, this will be e to the power minus I by. So, e to the power minus x into e to the power minus I y we get, and what we have here, I x minus y plus I c. So, this e to the power minus x minus I y is e to the power minus z, e to the power minus z, z is x plus I y. I we can write here, then x minus 1 upon I into y. So, that is x plus I y, and this we get as I z into e to the power minus z plus I c. So, we get the corresponding analytic function f z as I z into e to the power minus z plus I into c. Thus, we get the corresponding analytic function f z as I z into e to the power minus z plus I c, where c is a arbitrary constant, real constant. Okay. Now, let us take one more example on this. Suppose W is equal to phi plus I psi represents the complex potential for an electric field, and psi is given to be x square minus y square plus x upon x square plus y square. We want to determine the function phi. So, first you can show that psi x x plus psi y y equal to 0. First we show that psi x x plus psi y y equal to 0, or we can say del square psi equal to 0. Okay. Now, psi is can be differentiable infinite number of times with respect to x and y. So, the second order partial derivatives of psi are continuous functions of x and y, okay, and therefore, psi is a harmonic function of x and y. Psi is a harmonic function of x and y. Okay. Now, what we do, we want to find the corresponding harmonic function, conjugate harmonic function phi. So, we use the Cauchy-Riemann equations, phi x equal to psi y and psi x equal to, and phi y equal to minus psi x. So, using these Cauchy-Riemann equations, we can determine the corresponding function phi. It comes out to be phi x y is equal to phi x y equal to minus 2 x y plus y divided by x square plus y square. Phi xy is equal to minus 2xy plus y square. So, that is the corresponding plus a constant function, a constant c. Okay. So, first we show that psi is a harmonic function, then use the CR equations. By using CR equations, we have phi x equal to psi y and phi y equal to minus psi x. Then it turns out that we follow the same process as we have done in the case of example 1, and we see that phi xy is equal to minus 2xy plus y over x square plus y square plus real constant c. Okay. So, phi xy is equal to minus 2xy plus y upon x square plus y square plus c. So, we can follow the same process as in example 1 to arrive at this function phi. Now, there is an alternate method to determine the analytic function corresponding to a given harmonic function. It is known as Milne's method. Suppose we denote the partial derivative of u with respect to x by the function u1 xy, and the partial derivative of u with respect to y by another function u2 xy, then f prime z is given by u1 z0 minus I times u2 z0. This is the formula to determine the function analytic function fz. So, f prime z is equal to u1 z0 minus I u2 z0. Let us see how do we get this. So, to prove this formula, we know that f prime z, we have seen in the theorem on Cauchy-Riemann equations, where we proved that if fz is differentiable at a point z, then f prime z is given by ux plus ivx. Okay. So, we know that f prime z is ux plus ivx, and it satisfies Cauchy-Riemann equations because it is analytic. So, ux is equal to ux plus ivx is also equal to ux minus iuy, because uy is equal to minus bx. So, ux minus iuy, and ux we have denoted by u1 xy. So, we have u1 xy here and uy equal to u2 xy. So, f prime z is equal to u1 xy minus I u2 xy. Now, let us put y equal to 0 in this equation. Okay. If you put y equal to 0, then z is equal to x plus iy. So, f prime x plus iy, this is equal to u1 xy minus I u2 xy. Okay. So, putting x y equal to 0, we get f prime x equal to u1 x0 minus I u2 x0. Okay. Now, when y is equal to 0, z is equal to x, z is equal to x when y equal to 0. Okay. So, f prime x equal to u1 x0 minus I u2 x0. Now, let us replace x by z. So, we get f prime z equal to u1 z0 minus I u2 z0. Okay. So, this is how we prove this result. Now, this result can be used to determine the corresponding analytic function when the harmonic function u is known. Okay. So, let ux by equal to e to the power minus x, x sin by minus by cos by. Let us take the example which we have earlier considered. Okay. So, we found that the partial derivative of u with respect to x, this is ux. Okay. And partial derivative of u with respect to y came out to be this expression. Okay. By our notation, ux is u1 xy. So, u1 xy equal to this and u2 xy equal to this, which is equal to uy. Okay. Now, what we do, f prime z is equal to u1 z0 minus I u2 z0. So, in this expression, replace y by 0 and x by z. What do we get? u1 z0 is e to the power minus z into sin 0, which is 0, and here also we have sin 0. So, it is 0, here y is 0. So, this is also 0. So, u1 z0 equal to 0, and then minus I times u2 z0 is what? When y equal to 0, this term becomes 0 and this term becomes z into e to the power minus z. So, z e to the power minus z into cos 0 is 1. This term becomes 0 when y is 0, this term becomes minus e to the power minus z. Okay. So, we get f prime z equal to minus I into z e to the power minus z minus e to the power minus z. Now, we can find the integral of this function. Okay. So, f prime z is this. Okay. We can integrate that. So, f z is equal to minus I times integral of z e to the power minus z minus e to the power minus z dz. Okay. And this is minus I times integral of z e to the power minus z will be z times minus e to the power minus z minus integral of e to the power minus z dz, and then we have second term minus integral of e to the power minus z dz. Okay. So, this is minus I times minus z e to the power minus z. Okay. And here what we get when we integrate, this will be minus here. So, this will be become plus when we put minus e to the power minus z, and this will cancel with this. Okay. So, this plus some constant. Okay. Now, what is it? I z times e to the power minus z plus some constant. See, now let us look at the nature of this constant, whether it is real or it is complex or what. So, this constant is purely imaginary. Why? Because u x y, f z is u x y plus I v x y, f z is equal to okay. So, this quantity must be equal to u x y plus I v x y. Now, this means that this constant c does not have a real part, because u x y does not have a constant term, okay, and therefore, this c is purely imaginary. So, we can write this c as some I times another constant. Okay. So, we have f z equal to I z plus f z equal to I z times e to the power minus z plus some constant I times c dash. Okay. So, this is how we get the corresponding analytic function f z. Now, if you want to find the harmonic function, conjugate harmonic function of u, then that you can find from f z equal to I z into e to the power minus z plus I c dash by separating it into real and imaginary parts. Okay. By writing z equal to x plus I y and equating real and imaginary parts, we can find the function v x y. So, this Milner's method helps us in finding the analytic function associated with a given harmonic function. Let us now discuss orthogonal families. There is a very important, this is a very important property of analytic functions. Let f z equal to u x y plus I b x y be analytic in a domain D, then the real and imaginary parts of f z can be used to define two families of curves in D. They are called as level curves. So, the equations u x y equal to c 1 and b x y equal to c 2, where c 1 and c 2 are arbitrary real constants, are called level curves of u and b respectively. The level curves of these equations are define orthogonal families, that is, each curve in one family is orthogonal to each curve in the other family. That means, wherever they intersect, at the intersection point, the tangent to one curve is perpendicular to the tangent to the other curve. Say for example, let us look at this. Suppose we have one family of curves u x y equal to x u naught, and this is another family of another curve b x y equal to y naught, b x y equal to b naught. U naught and b naught are obtained from the fact that u x y equal to c 1 and b x y equal to c 2, they cut each other at x naught y naught. So, from that we can determine u naught. U naught is the value of u x y at x naught y naught. Okay. So, at a point of intersection z naught equal to x naught plus I y naught, where f prime z naught is not equal to 0. So, this is essential that at the point z naught prime f prime must not be 0. The tangent line L 1, this is tangent line L 1. Okay, this is tangent line L 1 to the curve u x y equal to u naught, and the tangent line L 2, this is tangent line L 2 to the other curve b x y equal to b naught, they are perpendicular. So, each curve of the one family is orthogonal or cuts the each curve of the other family at right angles. So, they are called orthogonal families. Now, let us prove this. How we prove this? We have one curve u x y equal to u naught. So, okay, so u x y equal to u naught gives us, when we differentiate this with respect to x partially, we get u x plus u y dy by dx equal to 0. dy by dx 1 means this is the slope of the tangent to the curve u x y equal to u naught at the point x naught y naught. So, this is minus u x over u y. These partial derivatives are being calculated at the point x naught y naught, that is at the point of intersection of the curves u x y equal to u naught and v x y equal to v naught. So, similarly, v x y equal to v naught gives in the same manner, when we differentiate it with respect to x, we get dy by dx 2 equal to minus bx over by. So, again here bx and by are calculated at the point of intersection x naught y naught. Now, the product of the two slopes dy by dx 1 dy by dx 2 is ux bx over uy by. Now, the function f z is analytic. So, Cauchy-Riemann equations will hold. Okay. So, ux will be equal to by. So, this ux and by will cancel, but uy is equal to minus vx. So, uy equal to minus vx gives us that ux bx upon uy by is equal to minus 1. So, by CR equations we get dy by dx 1 into dy by dx 2 equal to minus 1, and therefore, the curve uxy equal to u naught cuts the curve vxy equal to v naught at right angle at the point of intersection x naught y naught. Now, let us consider the function f z equal to z square. It is an analytic function for all z. Okay. And here you can see when we put z equal to x plus iy and then when x plus iy whole square gives you, using iota square equal to minus 1, we get x square minus y square plus 2ixy. So, here fz is equal to uxy plus ivxy when we write. Okay, equating real and imaginary parts, we get uxy equal to x square minus y square and bxy equal to 2xy. Now, when you take uxy equal to a constant, say C1, and bxy equal to another constant C2, that is, you find the level curves given by the equation uxy equal to C1 and bxy equal to C2. You can see that this is x square minus y square equal to C1 and this is 2xy equal to C2, or you can say xy equal to some other constant C3. Okay. So, this is a family of hyperbolas and there is also a family of hyperbolas. Okay. And each member of one family cuts each member of the other family at right angles. So, let us see that this you can see the families of curves x square minus y square equal to C1, 2xy equal to C2 are two families of hyperbolas. Since fz is analytic for all z, these families are orthogonal. We have just now shown. Now, these curves, okay, if you look these curves, so this one, okay, black curves, they are x y equal to constant, okay, while this other blue curves, they are given by x square minus y square equal to C1. So, at each point of intersection you can see tangent to one is orthogonal to tangent to the other. Okay. So, the two families of level curves are orthogonal to each other. With this, I would like to end my lecture. Thank you very much for your attention.